This video we're going to continue our look at advanced algebra parent functions. This is actually the second video on advanced algebra parent functions. If you want to find others, or if you don't see the one you want here, you might refer back to number 1 or even back to basic algebra parent functions if you want to see linear or quadratic. But assuming you're where you want to be, let's continue on and let's take a look at these parent functions. The first one we're going to look at is actually rather simple. It's the absolute value parent function. We want to see what characteristics it has. I'm going to do as I usually do. I'm going to create a little table over here to the right. Remember that all absolute value does is when you see these bars right here, they just tell you to take whatever number you get for an answer inside the bars and always make it positive. So if we look over here at -2, I'll go ahead and fill these in, it becomes +2. But if you look at +2, it already is positive, so it just stays +2. So any negative number becomes positive. Any positive number just stays that way. So when we graph this, here's the left side. This is the negative numbers and 0, everything above here. Notice that we go left 1, but then we go up 1. We go left 2, we go up 2, because the number turned into a positive number. But over here on the right side, 1 and 2, when we do that, they go over 1, but they still go up 1. They don't go down like a linear equation would. So the characteristic that we first want to notice is the graph makes a V. Sometimes if it's in the same family but not the parent, the V may be a lot skinnier, a lot narrower, or it could be even turned upside down. It may be placed somewhere else on the graph. That would just tell you it's a transformed version of y equals absolute value of x. Key characteristics: shape of a V. It always goes over and up the same amount. If it goes over 1, it goes up 1. If it goes over 2, it goes up 2. Even if that's left, -1 or -2. And then also we have the vertex point. The lowest point on the absolute value equation is at 0, 0. That's the parent function. So this one's pretty easy. Let's take a look at one that's a little bit more difficult. This is the exponential parent function, and in fact we're going to look at a couple of versions of this, but this b right here is what can make it a little tricky. That means base. We can pick any number that's positive that we want to go in there for b. We can use a number bigger than 1, or we can use a fraction between 0 and 1, and it'll have a little different effect. And each one of those in effect is a different parent function. So we could say that exponential functions have an infinite number of parents. Now we're only going to look at 2 of them, and then the rest will have similar characteristics. We first want to look at the ones that the parent is greater than, or the b rather, is greater than 1. Those will be exponential growth functions. And then we'll look at one where the parent b is between 0 and 1, which is a fraction. That will be an exponential decay parent. So let's just get started here by looking at, let's look at y equals 2 to the x. I picked 2 because it's bigger than 0. It's the first integer, bigger than 1 rather. It's the first integer bigger than 1. Pretty easy to work with. I'm going to go ahead and do a table of values down here. And notice that all I'm doing is I'm going to raise 2 to whatever power of x it is. Now if you forgot your exponent rules, if you want to do 2 to the -3, all that really means is that's the same thing as 1 over 2 to the +3. So that's equal to 1 over 2 times 2 times 2, which is 8. So when x is -3, y is going to be 1/8. So again, I have filled in this table for you. 1/8, and then 1 over 2 squared is 1/4. 1 over 2 to the first is 1/2, and then the regular ones, 1, 2, and 3. Now remember that anything to the 0 power, one of those fundamental rules of exponents, anything to the 0 power equals 1. So 2 to the 0 equals 1. 10 to the 0 would equal 1. Anything to the 0 power. So here's my table. And let's go ahead and graph this table by putting the points in and connecting them with a line. Let's look at it. Here's the graph. Notice that on the left side of 0, as the graph begins to go toward -infinity on x, notice what y does. the y values get smaller and smaller and smaller but approach 0, but they never get there. If you've watched the video or remember from rational functions, when you approach something but never get there, that thing you're approaching, that line, in this case the x-axis, is called an asymptote. That term is used in different ways, but this one is the horizontal asymptote at x, where x is, the x-axis is rather. Notice that on the right side of 0 on x, y begins to get larger and larger at an ever-increasing rate. It actually begins to approach infinity that way too. So one of the characteristics of exponential growth is that as you get smaller values of x, start to approach negative infinity, the y value gets smaller and smaller and approaches 0 but never reaches it. It has a horizontal asymptote that is the x-axis. But on the right side, the positive values of x, y also begins to get larger and larger and approach infinity. The other characteristic we want to notice is right here. Remember that because anything to the 0 power equals 1, the parent function will always cross the y-axis at 0, 1. The y-intercept's at 1. This is actually going to be true regardless of what we use for this base right here. So it's a defining characteristic of the parent function, in this case exponential growth. Now I want to do this again, but this time I want to do this with a fraction. I want to do y equals 1/2 to the x power. Now this may be even trickier for some of you. 1/2 and x is -3 on the first part of that table. All that means is flip the fraction over and make it 2 to the +3. What you're really doing is you're distributing the -3 to 1 and to 2. Well, 1 to the third power is just 1, so we don't need that on the bottom. And 2 to the -3rd power means it's now 2 on top, 2 to the +3rd. So this is equal to 8. Same thing with 2. It'll be 1 over 2 to the -1/2, which will be 2 squared, or 4. And so I can complete that table now. 1/8, 1/4, 1/2. Again, notice that when x equals 0, oh, did the wrong one, sorry. When x is equal to 0, that y is still equal to 1. Now here's the correct table at 8, 4, 2, and then 1. And then as we get bigger, 1/2 to the first is 1/2, 1/2 squared, 1/4, that's 1 squared over 2 squared, and so forth on down. Again, I'm going to graph this. This time the graph looks different. Notice it still crosses at 0, 1. That's still one characteristic, even if it's exponential decay this time. But this time to the left of 0, as x goes smaller and smaller toward negative infinity, y goes toward infinity. It gets bigger and bigger at an ever-increasing rate. But as x goes toward positive infinity, as it gets bigger on the right side, then it begins to approach but never reach the x-axis. So again, the x-axis is a horizontal asymptote, just as it was in the previous one, just as it was on 2 to the x, but this time the right side of the graph, or the positive side of the graph on x, approaches the asymptote at x, but the left side approaches infinity. So it's just the opposite of the growth function. Characteristics are still about the same though. It's still, this time it goes down from left to right before it went up from left to right. Still crosses at 0, 1 for the y-intercept. Still approaches x, but just from opposite directions. Another function that goes along with exponential is the logarithmic function. Now I chose a base of 2 here, and just like exponents, we could have used all kinds of different bases, but we're going to use this as a representative base because it's a pretty easy one to work with. You don't really have to remember all your log rules, but it would help filling out the table here. But if you remember how to find this, if x is equal to 0, we fill this in, y equals log base 2 of 0. What we're really asking is 2 to what power y is equal to 0? Well, you know what? There's not one. There's no power that we can raise any base to that's going to equal 0. So actually this is undefined right here. There is no value of y. And then we do the same thing. We say y equals log base 2 of, instead of 0, we say 1. put that in right there. And we say 2 to what power, instead of equaling 0 this time, is going to equal 1. Well, remember, anything to the 0 power equals 1, so that's 0. And then 2 to what power is going to equal 2? 2 to the first power does. 2 to what power equals 4? Notice I chose that carefully. 2 squared does. So there's my table whenever I do the log, remembering that 0 is undefined. Let me go ahead and fill this in where we can see it a little better. Undefined 0, 1, and 2, and I'm going to go ahead and graph that part of it. Now, I couldn't do anything with 0 because there is no point where x is equal to 0. There's nothing on the y-axis. Does that mean it stops at this point right here where x is 1 and y is 0? Well, no it doesn't. I need to break down the numbers more between 0 and 1. For example, what if x is 1/2? So we have y equals log base 2 of 1/2. The question is, 2 to what power equals 1/2? Well, it turns out 2 to the negative 1 equals 1/2. Remember, 1 over 2 to the first power, which is 1/2. So there's a point down there. There's another one at 1/4. We could say 2 to what power equals 1/4? Well, 2 to the negative 2 does that. So I can go ahead and fill in points that go past, to the left of, rather, that point where it crosses x at 1. And I'm going to do that right there. And I'm going to go ahead and connect those with a line. And here's what the graph does. Notice this time the graph is approaching y as x gets closer and closer to 0, but it never reaches it because 0 is undefined. It also never goes into the negative numbers. You don't take logs of negative numbers. So this is going to approach the y-axis. So we have a vertical asymptote that is the y-axis where x equals 0. So characteristics here look a little bit like the exponential. We learned in another video it's actually an inverse. Notice that they always have a point here that cross. This is the parent functions. They have a point that crosses at 1, 0. And this time, as x goes smaller and smaller, gets closer and closer to 0, the y value approaches 0 but never reaches it. So we have a vertical asymptote that is the y-axis. So that's the parent function for logarithmic functions. Again, we want to recognize parents because if we recognize the parent function, then we'll know if it's been changed, and we can learn rules that will allow us to write equations to make the adjustment to the equation itself to represent all kinds of functions that show that shape. If you didn't see the parent function you wanted here, there are other videos on parent functions on my website at MyMathEducation.com. They're arranged there by topic, as well as all kinds of videos. Also would invite you to subscribe to my YouTube channel at MyMathEducation. Appreciate you watching this one and hope it's been helpful. And if you want to watch other videos, I hope you'll come back here for more. Thanks again.